So welcome from my side, everybody. So as introduced, my name is Romain. I'm very happy and honored to be here with you today to give you some overview of my PhD dissertation that, as mentioned, was entitled Leveraging Synchronous Transmission for the Design of Real-Time Wireless Cyber-Physical Systems. So as you may know, cyber-physical systems are designed whereby we have computing elements that are interfaced with sensors, actuators, and controllers in order to interact with the physical world. Those type of systems are commonly deployed nowadays, but we are still envisioning larger scale systems that are ever more stringent requirements with respect to reliability, mobility, and scalability. In academic research, one often used cyber-physical system as a use case, a simpler use case, is an inverted pendulum, where, if I grab my laser pointer, whereby we have a ball depicted here that is mounted on top of a card. And this card can move left and right, and the goal of the task, of the control task, is to move the card in order to keep the pendulum upright. It's a fairly well understood problem and can be considered solved. However, things do get significantly more complex when we start separating the physical system we are trying to control from the place where we are executing the control or computing the control. And in the context of my thesis, I looked at the special case of these issues where the communication takes place over a multi-hop wireless network. What is important to understand in cyber-physical systems is that the application, that is the sensing, and the actuations, are setting the requirements for the system design. It means that, and my focus was on the communication side of things, and there we need predictability, adaptability, and remaining as efficient as possible. One key aspect to understand is that the guarantees we require are really defined end-to-end. That means that we don't only need to have strict guarantees on the time it takes for messages to cross over the multi-hop network, which is difficult in itself, but what we really need is to have end-to-end deadline guarantees, so that the time it takes to complete the complete loop between sensing, control, and back to the actuation. When I started my PhD, there has been previous work that obviously looked at such aspect, adaptability and predictability, but it was always either or. And none of those previous work had this design concept of end-to-end that I just mentioned. So the overall objective of my dissertation was to investigate whether we could design wireless systems that can provide such end-to-end guarantees while remaining adaptive and efficient. So we've used this toy example, this use case of an inverted pendulum, and you can see here a video of one of the experiments we conducted. So you have a wireless network on the right, and the pendulum you see on the top corner here is located here on one side of the network, and the controller is on the other side. And what we've been able to show is that we have guaranteed stability of the pendulum, even though the control is taking place over the network. And doesn't stop there, right? If we can grab this controller, then move around in the network, and if you look here on the pendulum video, you see no difference whatsoever. What it means is that mobility of the nodes are actually no effect at all on the control task performance. And here we move the controller, but we could have moved any node in the network as long as we have connectivity. From the communication standpoint, this has been made possible by the use of a technique which is known as synchronous transmissions. And the main claim of my dissertation is that this is a very well-suited technique for the design of real-time CPS. And here's an overview of the chapters of my dissertation, and due to time constraint, I will only talk about two of them. Starting with TTW, which stands for a time-triggered wireless architecture. So as I just said before, this was all made possible by the use of synchronous transmission, which is what? Essentially, this is a communication technique that takes place at the physical layer that enables a multi-hop broadcast based on flooding. This means that if I have one node depicted here in blue that want to send a message in the network, what this node will do is this broadcast its message, and then this message will be received by the two neighbor nodes that will repeat the message, and so on and so forth. And so the message will propagate in the entire network like in a wave. There are a number of tricks that are required to make this to work, but trust me, it does, and it's actually quite efficient. And most interestingly, for our purpose, synchronous transmissions effectively realized fast one-to-all communication or broadcast with extremely predictable timing. And because this timing is so predictable, actually what we can do is that we can take this entire floating process and encapsulate that into a box, like a time slot, a bounded time slot within which we know that we can achieve any broadcast communication. And so the way we will typically construct our communication protocols is that we would juxtapose a set of those slots. Right? They execute one after the other, and we bundle those in what we call communication rounds, between which we're going to turn off the radio so that we can save a maximum amount of energy. So that's the general structure that all communication protocols based on synchronous transmissions typically adopt. Now, based on that structure, if you want predictability, you need to do some real-time scheduling. Here is how it typically looks like. You have a number of messages that you're supposed to transmit, and those messages are available for transmission at some point. Those are the release times, and they need to be transmitted before certain deadlines. Now you can do some analysis to define what are the best times to schedule your communication rounds and then assign your messages to your rounds. That's all good in theory, but how do you know when the message deadlines are or when the messages are available for transmissions? If you think of it, actually, you will get this information based on the execution of the tasks. So if we go back to our pendulum example, what it means is that it's only once I know when I'm going to do my sensing, control, and actuation that I actually know when I can schedule my messages across the network. The bottom line here is that we need some sort of coupling between task and messages if we want to be able to guarantee end-to-end deadlines. There are several ways that this coupling can be done, and I investigated two of them in my thesis. And in TTW, the approach we followed is to use statically co-schedules all tasks and messages. So the way we've done this is by using a mixed integer linear program. So it's essentially a synthesis tasks. We specify all the constraints that need to be satisfied. We synthesize scheduling tables that are then executed at runtime. This is a well-understood technique that has been used successfully in wired network in the past. However, the key difference we have is that we have this concept of communication rounds. And while they are extremely useful to save energy, they also make the synthesis slightly more complex. The reason is that with rounds, we introduce constraints the like of messages must be served in a round that finishes before their deadline. And concretely, how would you specify this in a mixed integer linear program? Well, you would have something like this. The deadline D of a message MI need to be larger than the start time of a round J plus the length of that round. But that needs to hold true only if the message MI is assigned to the round J. And the issue, as you may already understand, is that both the assignment of messages to rounds and the start time of the rounds are variables of our problem. Therefore, such a constraint is nonlinear and cannot be trivially implemented and synthesized in a MILP. In my dissertation, I showed how such problems can be worked around using techniques inspired by network calculus. Unfortunately, I don't have time to get into more details now. At the end of the day, with such design, with TTW, we obtain extremely good predictability because everything is statically co-scheduled. It's also very efficient because we can optimize the scheduling table offline. for whatever purpose we have, in our case, low latency and low energy consumption. However, the adaptability is not as great because we're based on static schedules. Right? We can still adapt, and we've shown how to do this by using multiple modes. That is, we have different sets of scheduling tables between which we can switch at runtime. And in my dissertation, I showed how this could be done while still maintaining guaranteed end-to-end deadline even across mode changes. Now, we have our design, and usually then after the implementation comes the phase of the performance evaluation. Now, typically in such a case, you will define your scenario for your evaluation, and you collect some measurements, compute your metrics, and you're done. Or are you? You've run your performance evaluation only once. It's probably not enough, right? You're not really certain about your results. But how many times should you actually run this evaluation? Is 10 times enough, or 100 times? 1,000,000 times sounds like obviously too much, but how do you set the bar? Like, how much is enough? And it was the frustration triggered by the inability to answer that question that led me to work on what ended up being TriScale, a framework for supporting reproducible networking experiments. So why are we talking about reproducibility? What does it mean even? Informally, we can say that an experiment is reproducible if the same results are obtained when you repeat the experiment under the same conditions. And in low power wireless communication, we have a bit of an issue because the same conditions are essentially not possible to provide. Why? Because we are running a networking experiment in a real radio frequency environment. This is something that cannot be controlled, and we know that it has a strong impact on the performance of the systems we are testing. So we for sure cannot obtain the same results, right? Not exactly the same values. We know that performance variability is to be expected. And in my dissertation, what I found out is that we can actually classify different types of variability along 3 different timescales. The first timescale is the run. Like, you take your scenario, your protocol, you execute that, you measure certain quantity X, let's say energy consumption over time, you have some variation. Now, typically you would compute your metric based on that, for example, the mean of the measurements in your scenario. Now, if you repeat this run and you make a series of them and you compute your mean value every time, you're gonna get slightly different numbers. And so typically what you would do in your paper is that you would compute some sort of average, for example, the median, and you use that as a KPI, or key performance indicator. This is essentially the one summary that you do of your entire experiment. Now, the issue is that if you take that KPI value and then consider that you repeat your series of run later, 1 month later, or a year later, chances are extremely good that you will find slightly different values for those KPIs. And if you think of it, it's again a third layer of variability of performance for what is still the same system and the same experiment. So at the end of the day, when you analyze this structure, you realize that to design your experiment, you have a number of questions that need to be answered. How long should a run be? How many series? And how many runs per series, and so on. And the goal of my work, the goal of TriScale, was to try to find rational answers to those questions. And by rational, I mean that they need to make statistical sense. It's not like a rule of thumb kind of thing of like do 10 or do 20. No, that doesn't make sense. What we want is to be able to quantify the trade-off between how many runs we do, how much effort we put into our experimental campaign with the confidence we have in our results. And so in this talk, I will give one example of how we answered the second question. How many runs do we need in a series? So why do we do many runs? We do many runs because we want the KPI to be a robust estimate of our performance. If you think of it, the process we are doing is the following. We do a number of runs, which gives us metric samples based on which we are trying to estimate the underlying distribution of our metric values. And in general, we're not trying to estimate the entire distribution, but some moment of it, for example, the median. Now, the issue is that we will never know the entire distribution for sure, right? What we are trying to do is really an estimation of the median. And because we are doing an estimation, we are never really sure. So it doesn't make sense to report a single value. What we need to do is to report an interval. And in statistics, this is referred to as a confidence interval. It's conceptually, it's fairly simple. A confidence interval is a pair of numerical values in which the true value of some parameter, which the true value we don't know, lies within a certain probability, which is known as the confidence level. So on the right side, you have an example. If I say that AB is a 95% confidence interval for the median of my variable X, it simply means that the probability that the true median of X, which value I don't know, is between A and B with a probability which is at least as large as 95%. Now, which KPIs do we use typically? Often enough in papers, we tend to see the use of mean and standard deviations, which are two convenient statistics because they capture, they synthesize practically the shape of the underlying distribution. However, this is only true if we know that the data are coming from a normal distribution. And it's probably not a surprise to some of you that the data we are working with in computer science and in general in any experimental field tend to look, for example, more like this, but generally as non-normally distributed, which means that while you can compute mean and standard deviations, this view of the mind that we can many people have like deep-rooted in the back of our brain is actually incorrect. So we need to use statistical method in synthesis that do not make assumptions on the nature of the distribution. And therefore, in TriScale, we suggest to use as KPI percentiles of the distribution. And the reason we do this is that there exists a method that is non-parametrics, that does not make any hypothesis on what the underlying distribution looks like, for which we can compute confidence interval. Again, I don't have time to get into the details of the math, but one super interesting property of that method is that we can flip it around to extract the minimal number n of samples we need to make the estimation of any percentile P of P with any confidence level C. If you put in numbers into this formula and you look, for example, at the estimation of a small percentile with a standard confidence level of 95%, you'll find that you need about 300 runs in order to make such estimation. And this is one way from which we can directly, based on the definition of our KPI, answer rationally how many runs we need to perform. So this is one example of how TriScale fulfill this rationality of the experimental design goal. Now, concretely, how does that look like? If we go back to our TGW example, we have a model of how long the runs are, which we need in order to synthesize the schedule. Now, the performance evaluation question is the model actually providing a safe and tight upper bound of what's going on in the implementation? Now, the way we would do this is that we define our metric to be, for example, the maximum runtime measured across all nodes. And as KPI, we use, in this case, the 95th percentile and the 95% confidence level. Now, if we plug in the math with those values, we end up with, it returns that we need a minimum about 60 runs. So we perform multiple series of 60 runs each in order to perform this evaluation. And here is the results for one pair of parameters for our model. You see here the distribution of the data we've collected, the maximal value ever measured, and the model value. You observe two things. First, the model is larger than the maximum value ever measured, so we are indeed safe. And the numerical distances between the two, so about 300 microseconds, is fairly small, so we are also quite tight. Of course, it doesn't hold true only for one pair of parameters, but for the entire range of parameters we've tested. What it means is that based on this design and following that methodology, we can claim that with a confidence of 95%, the maximum runtime will be smaller than the model value in at least 95% of the runs. That's what we can claim. We can make a strong, statistically sound claim for those 95% of the runs. What happens in the 5 last percents? We have hypothesis. It's likely that the model will still be safe, but we don't know for a fact. However, for those 95%, we can make a strong statistical claim. And so to conclude on TriScale, we have bundled everything that is required to use the methodology into a Python package. And since the end of my dissertation, I have given already several tutorials on that topic, ranging from 1 to 3 hours long, and give a couple of invited talks. If you're interested to know more about this methodology, you can find all the code, papers, artifact, videos, and slides and so on the project webpage, triscale.ethstat.ch. This work I've conducted about TriScale was part of a broader initiative that was called IoT Bench, which was meant to set up and design benchmarking for embedded system or IoT, and we will focus on network embedded systems. So the general framework is similar to many other benchmarks. We would like a user to be able to send their program binary for evaluation, get some results back, and in parallel, storing those results so that we can compare the results of different protocols over time. And so here is where TriScale comes into play, right? It was really for the design of the experiments and the comparison of the results. Another concrete outcome of this IoT Bench initiative was the organization of a workshop series. The CPS IoT Bench workshops already took place 4 times, collocating with major conferences. And the 5th edition is actually happening in a few months, and it's currently seeking submissions. So if you have done benchmarking related activities in embedded systems, check it out. You will find it a very interesting venue for your work potentially. With this, I'm already at the end of this very short and high-level overview of my PhD work. If you're interested to find more details, all code, documents, and software are all publicly available in my GitHub. So feel free to check it out or reach out for more detail. With that, I hope you've enjoyed the talk, and I'm now ready to take any questions.